In this video, we're going to discuss complex numbers. Real number system can be extended to complex number system by defining the square root of -1. Complex number system is the biggest set of numbers we know. Real numbers, all real numbers are part of complex number set. This is especially useful when we learn fundamental theorem of algebra, which states that any polynomial of degree n has n solutions. Not all Some may be complex solutions. Not all solutions have to be real solutions. So there is no real number whose square is less than 0. We know that there is no real number which multiplied by itself will give me -81, because 9 times 9 gives me +81, and -9 times -9 also gives me +81. Square root of a number is the number which multiplied by itself gives you that radicand. So in this case, there is no real number that multiplied by itself will give me -81. Thus, we're going to take help of complex numbers here and define the complex number imaginary unit, I. I comes from Greek letter iota. I is equal to square root of -1. Okay, so I is square root of -1. Remember that, memorize that. If I go ahead and square both sides, I would have I square equals -1. And if I go ahead and multiply both sides with I, so I squared times I would be -1 times I. This gives me I to the third power, because exponents get added, equals negative iota. So that's I to the third power equal to. And if I multiply both sides with the I again, or we can just look at, for this one, I square is -1. If I go ahead and square both sides, then it leaves me with I to the fourth power is +1. So memorize these powers of I. One of the previous students has told me that his previous instructor said that, remember, I1, I1. So I1 and I1, and the middle two are going to be negative. I1, I1, and the middle two are going to be negative. He said, remember I1, I1, so I square, I to the third, I to the fourth. On the right hand side, I have an I, which is square root of -1, and then -1, negative iota, and a +1. I to the fourth power is +1. Just like we have the real plane, xy plane, we also have the complex plane, and we can graph complex numbers, which you will learn in trigonometry when you take trig course. Memorize these, as you will need to use them when we are simplifying powers of I. Okay, so we're about to simplify a few powers of I. Keep in mind, I'm going to be using this property over and over. My goal will be to break the exponent so that I have multiples of 4 aside, because I to the fourth power is 1. I'm going to try to use that fact, okay? So I to the 6, I'm going to write it as I to the fourth times I squared, okay? Because we know we can add the exponents, and that is equivalent to I to the 6. I do know I to the fourth is equal to 1. So when I multiply something with the 1, it doesn't really matter. This is just 1. And I square is equal to -1. That turns out to be -1. 1 times -1 is -1. Next, we have I to the 10th power. I'm going to break it as I to the 8th times I squared. Again, I to the 8th is I to the 4 to the second power times I squared. I to the fourth is 1. 1 to the second power will be still 1. So it's like 1 times I square, which is going to be -1, because from my table, I know I square is -1. And -1 times 1 is still 1. Next, we have I to the 15th. I'm going to break it so that I can write it as I to the 12th times I to the third. Well, any exponent that is multiple of 4 is going to become 1, because I can express it as I to the fourth to the third power times I to the third power. Because the rules of exponents say that these two exponents will multiply 4 and 3, and this is going to become I to the 12th. Now, I to the fourth is 1. 1 to the third power is still 1 times I to the third. So 1 to the third power is still 1, and I cubed is equal to, I'm going to look at the table now, I cubed is equal to -I. So this simplifies to -I. I to the 28th power, let's write it as I to the 4 to the 7th power. I to the fourth is 1. 1 to the 7th power is 1. I to the 51st power. Again, my goal is to break it to have a multiple of 4 in there, because that's going to be really, really helpful to me. I already know that I to the 4th power is 1. So I'm trying to use that fact to make my life easy. So this turns out to be I to the 48 times I to the 3rd power. I to the 48 can be written as I to the 4th to the 12th power and I cubed. From now onwards, I'm just going to start disappearing any multiples of 4 exponent of I, because it's just 1. 1 to the 12th power is still 1. We know that. We don't need to really write it down. And that's just 1 times I cubed is negative I. So my final answer turns out to be negative I. And I just use this from the table. So remember the first 4 powers of I. Using those first 4 powers, we can find any powers of I. Keep in mind, my goal is to break the exponent so that I have a multiple of 4, because I to the 4th power is 1. And also notice any even powers are going to turn into 1 or negative 1. And odd powers are going to be turned into I or negative I. Okay, so let's check out number 6 here, I to the 45. Let's break it as I to the 44 times I. And this I already know will be 1, because we can write it as I to the 4 to the 11th power. 1 to the 11th power is still 1, so that's equal to I. I to the negative 24, the negative exponent means bring it to the bottom and make it positive. And this can be written as I to the 4 to the 6th power, which is just going to be 1. I to the 20th plus I to the 10th power. Let's think about that. I to the 20th is I to the 4 to the 5th power. And I to the 10th power, we can write it as I to the 8th times I squared. Okay, I to the 4th is 1. 1 to the 5th power is still 1. And I to the 8th power can be written as I to the 4 square times I square, which is 1 times negative 1. So this turns out to be 1 minus 1, which is 0, because we have a plus in the middle. 1 minus 1 will be a 0, because positive times a negative is a negative. All right, next example, we have, I'm going to clean up, give myself a little more room, and ignore the page number. That's not needed. Negative 3I to the 5th power. Well, negative 3I to the 5th power, we can write it as negative 3 to the 5th power, I to the 5th power. Negative 3 to the 5th power is 3 times 3 is 9 times 3 is 27. 27 times 3 is it 300? 3 raised to the 5th power is 243. So this is going to be negative 243. And I to the 5th can be written as I to the 4th times I, which I to the 4th is 1. So it's negative 243I. Okay, more examples. So here's a definition of complex number. A complex number is a number of the form a plus bi. And this I is same as square root of negative 1, where a and b are the real numbers and I is the imaginary unit. The a is called the real part and b is called the complex part or imaginary part. A is called the real part of this complex number. B is called the imaginary part of the complex number. The standard form of writing a complex number is a plus bi. A pure imaginary number is a complex number of the form bi. So your real part can be 0, the imaginary part can be 0. Remember earlier, I did say that all the real numbers are part of complex numbers. All real numbers fall in the set of complex numbers. So if your real number is 7, you can write it as a complex number by using 7 plus 0i. So your imaginary part will be 0 here, real part would be 7. All real numbers are a subset of complex numbers. Evaluating square root of negative numbers. Let's go ahead and simplify some square roots of negative numbers. Earlier, we saw the product rule of radicals that said we can either split a radicand into 2 separate radicals or multiply 2 separate radicals into a single radicand as long as the indices are same. So we're going to be using that property here. We're going to break it into square root of 25 and square root of negative 1, which will be 5i. And square root of 2 would be I root 2 or root 2i. Okay, we can write it as root 2i or I root 2. I is not inside the square root. Square root of negative 48, I'm going to break it as square root of 48 times square root of negative 1. And 48 is 16 times 3, and that's going to give me 4i root 3. 4i root 3 because I comes from the imaginary unit. Square root of negative 81 is going to be 9i. Root 2 times root 6. So here, first of all, we have to first of all take care of before we can use the product rule, we need to take care of the i's. We need to take care of the negatives inside the radicals. So I'm going to be pulling out. So that's what I'm dealing with. So we can multiply the imaginary. So this is I root 2 times I root 6, which is I square root 12. Now let's simplify it a little. I square is equal to negative 1, and root 12, we can break it as 4 times 3, and I can pull a 2 out. So the 2 will be multiplied with so it's going to be negative 2 root 3 once we simplify it. Okay, next we have root 3 times square root of negative 27, which will be, I'm going to pull out the I first, and now I have 3 times 27 in the square root, which is I, and 27 is 3 times 3 times 3 times 3. So I can pull 2 3's out, which is going to be a 9i. Okay, next we have square root of negative 40. Again, pull out the radical before you can use the product or quotient rule. So we are left with I root 40 over I root 8, which is I root 8 times I root 5, I root 8. Let's go ahead and cancel the common factors. Turns out to be we can also cancel the common factor. We're only left with square root of 5 here. Everything else cancels. Square root of 5 is all we're left with. Okay, next, the arithmetic of complex numbers. Now we're going to talk about adding, subtracting, multiplying, dividing complex numbers, okay? To add complex numbers, we add the like terms, means the real parts get added together. So if we are trying to add two complex numbers, a plus bi and c plus di, then we add the real parts together and we add the imaginary parts together, and we leave them in the form of a plus bi. To subtract the complex numbers, the same kind of story. Don't forget to distribute the negative sign inside first, and then take care of adding the real parts and adding the imaginary parts or subtracting. So here we're going to focus on a couple of examples where we're adding or subtracting the complex numbers. 2 plus 3i plus negative 6 plus 7i. So add the real parts together. 2 minus 6 is negative 4. Add the imaginary parts together. Negative 4 plus 10i. Again, it's a plus. So first of all, I'm going to try to write them without parentheses and also using the complex numbers. Square root of negative 36 is 6i, and square root of negative 49 is 7i. Add the real parts together, which is 7. Add the imaginary parts together, which is 7 minus I. In the next example, I have a subtraction sign. Be extra careful when you're dealing with the subtraction problems, because everything that comes after the subtraction sign will turn into an opposite. Okay, so first I took care of distributing the negative, and now add the real parts together and add the imaginary parts together. To multiply complex numbers, use the distributive property, then combine like terms using FOIL. One thing to keep in mind, the product property of radicals does not apply when radicand is a complex number. So evaluate the square root of negative number first, then multiply the radicals. Let's check out some examples. So number 11, we are going to multiply these two complex numbers. Both are complex numbers. So first, outer, inner, last. Okay, first times first. Root 3 times root 3 is minus 2i root 3 plus 2i root 3 minus positive times negative is a negative. 2 times 2 is 4, and then I square. Okay, so root 3 times root 3 is root 9, which is equal to 3. These are same terms with opposite signs. They will cancel. Minus 4i squared. From the table, we remember I squared is -1. So this turns into 3 plus 4, which is 7. Sometimes the homework systems actually, even if they don't, because we started with a complex number, we want to give our answer in the form of a complex number. So 7 plus 0i is what we would leave it with. Okay. Next example, number 12. Square means we have two of these, 6 minus 3i times 6 minus 3i. That's what square means. First times first is 36. Outer times outer is negative 18i. Inner times inner is again negative 18i. Last times last is 9i squared. So 36 minus 18 and 18 is 36i. Minus 9, because I square is -1. So when I replace the I square by -1, 9 times -1 turns into -9. 36 take away 9 is 27 minus 36i is what we're left with. Number 12 looks a bit complicated. Looks like there's a lot going on in number 12. I have subtraction going on, and I also have multiplication going on. So take it step by step, do it slowly. More chances of making mistakes if you rush. Okay, so I'm going to start by, PEMDAS says multiplication comes before adding or subtracting, so I'm going to take care of multiplications and then take care of subtractions. Okay, first times first, 2 times 4 is 8. Outer times outer is negative 10i. Inner times inner is positive 12i. Last times last is negative 15i squared. Minus, in the second parentheses, first times first, 7 times 8 is 56, minus 63i plus 48i minus 54i squared. Let's clean up inside the parentheses and then take care of the subtraction. Okay, there's the two like terms, and I square is equal to -1. We know that. I square is same thing as -1. Because I is square root of -1. So 8 plus 2i plus 15, because negative times negative will turn into positive. And now we have 56 minus 63 minus 48 would be 15. 15i plus 54. Okay, now a little bit more cleaning up. 15 plus 8 is 23. 23 plus 2i minus 56 plus 54 is 110 minus 110 plus 15i. You might say, why did I turn 15 to positive? Don't forget, every time I distribute a negative, everything inside changes. So I first added 56 and 54, which turns into 110, and -1 distributed into 110 gave me a -110, and -1 times -15 is positive 15i. 23 plus 110 is going to be 133 and plus 17i. 133 plus 17i is all we are left with. Okay, and let's double check if that is correct, because there is a lot going on here. 8 minus 10i plus 12i minus 15i squared. Okay, and that's plus 2i. 8 plus 15, 23 plus 2i. That's absolutely right. And then we have 56. 9 times 7 is 63i plus 48i minus 54i squared, which will be positive 54. 56 plus 54 is 110, and that's going to be negative 15i, and that negative 15i turns into positive, and 110 turns into negative. Looks like 133 plus 17i. Okay. All right, next, to divide complex numbers. Last operation on complex numbers we will be looking at. To divide complex numbers, multiply the numerator and denominator by conjugate of denominator. Okay, then multiply and simplify. So our goal would be to multiply numerator and denominator with the conjugate of denominator. For example, in this case, we are dividing this complex number. Remember, complex number is a square root, and we are not allowed to leave a square root in the denominator per algebra norms. So my goal is to remove the square root from the denominator, and the only way I can remove this square root from the denominator is if I multiply both numerator and denominator with the conjugate. Let's see a couple of examples. The first one is worked out. Let's start by doing example number 2, okay? So here, I'm going to multiply numerator and denominator with the conjugate. We've talked about the conjugate earlier. Conjugate of a plus b is a minus b. Conjugate of negative a plus b is negative a minus b. Conjugate of a minus b is a plus b. Conjugate of negative a minus b is negative a plus b. Okay, so you just change the middle sign to get a conjugate. So here we are. In the numerator, I'm going to have to FOIL 3 plus 5i times 1 minus I. In the denominator, I can use the difference of squares because a plus b times a minus b is equal to a square minus b square. So here I'm going to have 1 square minus I squared. Okay. Now I'm going to try to get rid of these a plus b and a minus b from here. Let's see. All right, so go ahead and FOIL in the numerator. So it leaves me with 3 minus 3i plus 5i minus 5i squared divided by 1 minus I squared is equal to negative 1. And that is going to be 3 plus 2i plus 5 because I squared is negative 1. And then we know this I square is equal to negative 1. Negative 5 times negative 1 would be a positive 5. In the denominator, we would have 1 plus 1. So it turns out to be 8 plus 2i divided by 2. We can pull out the common factor 2 from the numerator and cancel with the denominator. So 4 plus I is what we are left with. All right, 6 minus I times 2 plus I turns out to be multiply numerator and denominator with the conjugate. Let's go ahead and FOIL the tops, FOIL the bottoms, and see where do we end up. 6 minus I, 6 times 2 is 12, minus 6i minus 2i plus I squared over a square minus b square, which is 4 square minus I squared. So let's go ahead and replace all the I squared. We know I squared is equal to negative 1. We have seen the powers of I because I is equal to square root of negative 1. If you go ahead and square both sides, I squared turns out to be negative 1. So we are left with 12 minus 8i minus 1. No need to put the parentheses here. 12 minus 8i minus 1 over 4 minus negative 1. 4 minus negative 1. Yep, I square is negative 1. So that turns out to be 11 minus 8i over 4 plus 1, which is 5. Because negative and a negative will become a positive. Okay. In the next video, next example, we have 6 plus 8i over 3i. We